Today I'm going to go over section 2 from chapter 5. The title of the chapter is Producing Data. The title of the section is Designing Experiments. So in this chapter we've got 3 sections: designing samples, designing experiments, and simulating experiments. We've gone through designing samples. Let's talk a little more about designing experiments. First of all, the difference between an observational study and an experiment is that in an experiment, a treatment is imposed. It's a great phrase to memorize. Treatments are imposed in experiments. In an observational study, there is no imposition of treatments. We simply observe. Some students erroneously think we observe in an observational study and we don't in experiments. Of course you observe in an experiment. The difference is in the experiment you're actually requiring the subjects or experimental units to do something. And so that leads to the next term. Subject or experimental unit is someone who has a treatment imposed upon them. If it's a person, we usually call them a subject. If it's a rat or a tire or a tree or a car or something else, then we typically call those experimental units. A placebo is a dummy treatment that has no known physical effect, but it might have a psychological effect. And so sometimes we give patients placebos, commonly referred to as sugar pills, to see if there's any difference when you receive a sugar pill versus, say, a real aspirin or some actual medication. There are 3 principles of experimental design. The first is to control the lurking variables. I'll try to give you an example that'll tie these 3 things together. The second is to randomly assign treatments to the experimental units. And finally, to replicate each treatment on as many units as possible to reduce chance variation in the results. I'll give you just a moment to jot these 3 things down. Control the lurking variables, randomly assign treatments to experimental units, and then replicate the treatment on a number of units to reduce the chance variation. For example, if I'm giving people apples to determine whether or not that helps reduce the number of cavities, it becomes an experiment when I impose a treatment, when I no longer simply observe whether people are eating apples, but now I'm giving people apples to eat and perhaps restricting other people from eating apples. I want to randomly assign my treatments to the experimental units so that I don't allow the, say, healthier people to choose for themselves to take the apple and the less healthy people to choose to avoid the apples. Finally, I want to replicate this on as many units as possible. When I get to the end of the experiment, if I've controlled the lurking variables, if I've randomly assigned treatments, and then I find a difference, that difference is due to one of 2 things. I just got lucky, or perhaps unlucky, depending on your point of view, in the way that I assigned the people. So maybe the people with better genetically better teeth ended up in the group with apples just by chance. Or it turns out that it is the apples that reduce the number of cavities. In order to minimize the likelihood that you just randomly get lucky by putting the healthy people overwhelmingly in one group, you replicate the treatment on a number of units so that it's unlikely that you would get repeatedly lucky by continually putting those people all in the same group. We'll explore these principles some more in the next few days. Experimental design covers these 3 ideas as well: factors, levels, and treatments. Factors are the explanatory variables that the experiment covers. The levels are the different values that the factors can take. And the treatments are the individual different things that need to be imposed to the experimental units. Perhaps a couple of examples are in order. Suppose that I am a marketing major and I'm working on a new advertising campaign to sell a product. Let's say that I came up with 3 different versions of a commercial. One version of the commercial is 15 seconds long. One version of the commercial is 30 seconds long. And then I have one of those really long 90-second commercials that I've designed as well. I'm going to put these commercials in the next showing of perhaps Survivor. I might show the commercials 1 time, or I might show the commercials 3 times. Suppose I recruit some volunteers to watch the episode of Survivor. Some of them watch the episode with the 15-second commercial once. Some people see the 30-second commercial once. Some people see the 90-second commercial once. Some people see the 15-second commercial 3 times. A group sees the 30-second commercial 3 times, and a group sees the 90-second commercial 3 times. Then at the end of all of it, I ask them for their opinions on my product. In this example right here, we have 2 factors: the length of the commercial and the repetitions of the commercial. There are 3 levels to the length and 2 levels to the repetition, giving me a total of 1, 2, 3, 4, 5, 6 different treatments in this example. At the end of my experiment, I would re-examine the thoughts or the opinions that these viewers had of my product. If it turned out that their opinions changed quite a bit, it's either just a fluke or it's a result of this experiment, of the treatment that I've imposed. If that difference, the difference in their opinion, is too large for me to reasonably attribute to chance, if I think it's more than just getting lucky, then I call that statistically significant. Statistically significant results occur when the observed effect is too large to be reasonably attributed to chance. If I randomly divide 2 groups of students into 2 different teachers' classrooms, I don't really expect for their results to be identical. One teacher, just the way it goes, is probably going to have students that end up a little better than the other class. However, if that difference is dramatic, if it's large enough to where I no longer think it was just luck of the draw, we call that difference statistically significant. Another thing we can use for experiments are the concepts of blind and double-blind experiments. In a blind experiment, the person receiving the treatment doesn't know what treatment they're getting. So I don't tell the patient whether it's a real pill or a placebo. In a double-blind experiment, neither the person receiving the treatment nor the person giving the treatment knows what the treatment is. In other words, my administrator, whoever's administering the experiment, gives me a pill to take to Mrs. Jones. I don't know if the pill's a sugar pill or the real thing. Mrs. Jones doesn't know if the pill is a sugar pill or the real thing. Clearly, my administrator knows, but my administrator doesn't have direct interaction with the subjects in this experiment. That way, I don't give it away through my body actions or through other things that I've got going on. I don't know, the patient doesn't know. Everybody who's directly involved or interacting with the subjects is ignorant as to what is really going on as far as which group somebody is involved with. This also helps with a very serious problem in a lot of experiments, the lack of realism. If I get a group of people together and I ask them to watch an episode of Survivor so that they can tell me what they think about these products at the end of the commercials, then they're going to watch commercials in a way that's different than they normally would in their living room at home. Figuring out ways to overcome the lack of realism is a very important step for researchers. There's at least 3 different types of experimental design. One is called a completely randomized design. I take my group that I'm going to perform the experiment on. Maybe I number them all from 1 to 60. I randomly assign the first 20 of them to group A, the next 20 to group B, the other remaining 20 to group C. Perhaps I put all their names in a hat. The first 20 I drew out went in this group, the next 20 go to that group, the remainder goes to this group. This is a completely randomized experiment. The next type is called a matched pairs design. In a matched pairs design, I attempt to find two subjects or experimental units that are very, very similar, and then I randomly choose one of them to go in this group and one of them to go in that group. Likewise, I could have a matched triplet design, I suppose, where I get three subjects that are very similar in whatever characteristic I'm looking at, and I put one of each in each of the three groups. So if I'm doing an experiment on how aspirin affects heart attacks, maybe I want to find three subjects that are all middle-aged men slightly overweight with stressful jobs. One of them gets in this group, one of them gets in that group, one of them gets in the other group. That way I ensure that each of my groups, each of my experimental groups, is similar to the other group. The third type is a block design. A block is a group of experimental units or subjects that are known ahead of time before the experiment to be similar in some way that I think will affect the response to the treatments. In a block design, the random assignment of units to treatments is carried out separately within each block. So for example, suppose that I want to give people an aspirin to see how it affects their likelihood of having a heart attack. But I think that it might affect men and women differently. Since I think that that's going to be a factor and I want to control it, I can put all my men in one block and all my women in another block. Now, within the men, I randomly decide which ones are going to get the placebo and which ones are going to actually get the aspirin. And within my women, I figure out which ones are going to get the placebo and which ones are going to get the actual aspirin. So I basically break my experimental group up into different parts. A picture would look like this. I have a large group of people, subjects. I think their gender is relevant to the particular study I'm doing, so I break it up. I put the men here and the women here. It's important to note and obvious to note that was not a random assignment. The men went to one side of the room, the women went to the other. Now I'll do the random allocation of treatment. Within the men, perhaps I flip a coin. If they get heads, they get the real treatment. If they get tails, they get the placebo, which I would call treatment 2. Do the same thing for the women. Randomly decide which ones get treatment 1 and treatment 2. And then I'm going to compare the men. I'll compare the women. And I can decide that aspirin helped the men. Maybe it didn't help the women quite as much. The blocking helps reduce the variability that would be injected into the experiment due to the gender of the subject. I'd like to give you one more example that might help some of you. Suppose that I have a new diet that's going to increase the weight that a rat can put on over a 28-day period. I have a big group of rats that I'm going to use for my experiment. I randomly divide the rats into two groups, group 1 and group 2. Perhaps there were 30 rats in my original group, so now I've got 15 rats here and 15 rats here. Now group 1 is going to receive the standard food or the standard diet that they've been receiving. Group 2 is going to get the new and improved diet. Hopefully, by randomly dividing the rats into two groups and then treating those two groups identically, except for the type of food they get, I've controlled the lurking variables that might go on. Now, I randomly assigned them into groups. I replicated it on a group of 30 rats, and finally, I'll compare the results. In this case, I've got one factor, the food that they're going to receive, and it's got two different levels, the old food and the new food. We'll continue along with some more examples out of section 2. Try to put a little bit more realism into this and some actual examples that you can see how all this plays out.